Hello, everybody, and thank you for joining me. We're on what I believe is... question 6. This is the last question of the 2017 Midterm 2 that has been provided on OWL. So we've got 5 marks on offer for this question, so not nearly as, let's say, important as some of the others in terms of people who just care about their marks. What we've got are a series of true or false. We just need to circle true or false. We don't actually need to show their work. I'm going to provide a little bit of a justification, because I'm not actually writing this test, so I can take a little bit of time and talk about it. Alright, so we can scan, see if there's anything in particular that grabs us, but I'm just going to start with 1 here. So if AN is a convergent sequence, then the sequence e to the 2 minus NAN converges. Okay. So if AN is convergent, then we've got this sequence, and it's also convergent. Well, unfortunately, I don't have like a calculator or anything to mess around with, but so I can't just sort of pluck a sequence out of thin air and check to see if it works. Now, e to the 2n or 2 minus n on its own, if I called that another sequence bn, as n gets closer to infinity, e to the 2 minus n, and therefore our b's, is really just e to the 2 over e to the n. And I seem to recall in one of the questions I remarked that if you have sort of a constant fixed thing and an exponent in the bottom is just going to get bigger and bigger and bigger, so this is just going to head to 0. So the bn's converge. I know the an's converge. The question is, does the product converge? And this was actually a result we learned in class. If the limit of the ANs is L, I don't know what it is, but I do know it's convergent, so it has a limit. And the limit of some BNs is M. In this case, I know it's going to be 0, but I'm just citing the result. Then it turns out the limit of the product exists, and it's equal to LM. So does this brand new product sequence converge? Absolutely. It converges to L times M, which no matter what you're looking at will have to be 0, because anything times 0 is 0. So I'd say this one here is true. Alright, B. So these guys tend to leave their stuff off, and that's okay. As I've mentioned in class, well, at least in my class, if you're worrying about the indices, you're doing a little something wrong. Okay? That's not what really this is all about. It's certainly not about, do I start at n equals 1 or n equals 2? None of that sort of stuff. So basically what we're saying, suppose I have a divergent series. Let's underline that a bit better, shall we? Suppose I have a divergent series, then I have either the limit of the ANs isn't 0, or the limit of the ANs does not exist. So for this question, they're trying to make you remember, oh, there was that result that said, if the ANs converges, then the limit of the ANs must be 0. They're trying to say, well, if the limit of the ANs isn't 0, or doesn't even exist, then you're divergent. That's what the reverse of this statement is, but they're saying something slightly different. They're saying, if you're looking at a divergent series, there's no way the limit of the ANs is 0. And this is something we've brought up. Both classes will have brought this up. The harmonic series is a fantastic example that it's a divergent series, but the limit of the terms is 0. It's not the only example, but it's sort of the best one. So it diverges and the limit's 0, but they're saying true or false, if you've got a divergent series, then the limit can't in any way be 0. Well, this is false. We've got one. And all it takes is 1 to disprove a statement. It's called a counterexample. Okay, you can find more, but if somebody comes along and says something to the effect of, all sheep are white, to prove that correct, you're going to have to use some, grand unified sheep theory. Either that or go everywhere in the world and, take a picture of every single sheep. But to show the statement, all sheep are white, is wrong, it just takes one black sheep. All I need is one black sheep that find that, present that to the Institute of Sheep Sciences, and suddenly the all sheep are white result is disproven. This is a counterexample. We have a counterexample. The harmonic series diverges, but the limits of the sequence is 0. Okay. All right, C. This series here is convergent. Okay, it's got a lot of factorials in it. Certainly a lot of factorials. Now, the 2n factorial is much bigger than n factorial and n plus 1 factorial. So I'm thinking this is probably true. But probably true and true are different things. So let's see if we can get some theory to back this up. Now, the presence of factorials always makes me think ratio test. So what have I got? My ANs here are n factorial, n plus 1 factorial, and 2n factorial. And how do I get the next term? Anywhere I see an n, I put an n plus 1. So n plus 1 plus another 1 is n plus 2. And 2 times n plus 1 is 2n plus 2. Okay? So we're going to get our row and ask, all right, talk about the limit of the an plus 1 over the an. And this is going to be n plus 1 factorial, n plus 2 factorial over 2n plus 2 factorial, all divided by n factorial, n plus 1 factorial, and 2n plus 2 factorial. Oh, 2n factorial. My mistake. All right, so invert and multiply, and we're going to collect like terms. So the n plus 1 factorial and the n factorial, I'm going to group them together, n plus 2 factorial and the n plus 1 factorial, and then the 2n factorial over the 2n plus 2 factorial. Okay, and then we'll get, I can separate this a little bit. Normally I wouldn't, but again, I don't have to go fast, so why bother? We learned in class we can separate these out. Factorials have a nice recursive formula. And we'll keep the 2n. 2n is smaller than 2n plus 2. I'm going to have to break him apart twice. But there we go. And now, oh, look at that. So many things cancel. And I'm left with the limit, n factorial of n plus, as n goes to infinity, n plus 1, n plus 2, 2n plus 2, 2n plus 1. Now we can do other things, simplify this in many ways. This is a polynomial over polynomial. In fact, it's quadratic over quadratic. So if you want to, you can just expand it out. Okay. Other things you could do, well, n plus 1 divided by 2n plus 2 is going to be 1/2. So that'd be something else you could do. But I'm actually just going to expand these out. So n squared plus 3n plus 2 over 4n squared plus 2 times 2, 2 times 1, so plus 6n plus 2. And in the limit, we get just a quarter. Nothing fancy. We don't need to show our work. So 1/4. But 1/4 is my row value, and that's less than 1. That means convergent. So we're done. Well, we're not done. We've got D and E left to go, but we're done C part at least. Okay. So D1. If the series Cn x to the n, so some sort of power series centered at 0, or Maclaurin series, as we've learned, has radius of convergence 2, and the series Dnx to the n, another power series, another Maclaurin series, has radius of convergence 6, then the series Cn plus Dnx to the n has radius of convergence 4. So this is a little suspicious. We don't talk a whole lot about radii of convergences and how they mix when you add and subtract. And the reason we don't really dwell on this, we do talk about it a little bit. The textbook has some questions related to it. But if we ask that question, then some people come along and ask about, well, what about multiplication and division? And those are weirder stories. Okay. So with this one, well, what does the radius of convergence mean? And all these power series are centered at 0. Now, if I know that the radius of convergence is 2, then anything that's within 2 of 0 will make plugging in x within 2 of 0 will make this converge, provided it's not the endpoints. -2 and 2, we don't know about those ones yet. Okay, so if this were true, then, well, 3 is within 4 of 0. So then what could I have? Well, then this would converge, right? Since the distance from 3 to the center is less than my radius. And you know what else would be true? dn 3 to the n would converge. Why? Well, 3 is within 6 of the center. But having a radius of convergence of 2, I know for a fact the way a radius of convergence works is if I'm further away than 2, I guarantee you I will not be able to converge. So if I plug in 3 to the series with CNs, I get diverges. And that's because 3 minus 0 is strictly bigger than my radius. But if this were the case, well, I can rewrite this very, very carefully. Okay. I'm adding a dn 3 to the n, and I'm subtracting a dn 3 to the n. No change there. But then I've got... I can separate this out a little bit. But each of these converges. And we learned in class that the difference of convergent series is also a convergent series. So then Cn 3 to the n converges. But I already said it diverges. So we can't have a radius of 4. We just can't. Okay? The best we can have is a radius of 2, and you can actually show that when you add and subtract, you just sort of take the minimum radius of convergence, provided everyone's centered at the same place. But this one here, he's false. He's false. Okay. So the last one, E, and this is going to finish up the midterm for us. The series n factorial x minus 1 to the n has a radius of convergence of 1 over root 2. So this is interesting. It's a power series not centered at 0. It's kind of nice. Good change of pace. But has a radius of convergence of 1 over root 2. Now, how do we find radii of convergence? Right? We use one of the root or ratio test. Again, because of the presence of n factorial, I'm probably going to use the ratio test. Ratio test. Although having only one n factorial in there, provided we know the limit of the nth root of n factorial, this probably wouldn't be so bad. Okay? But I'm going to use ratio test, so an plus 1 is n plus 1 factorial, x minus 1 to the n plus 1, an divided by an, and that's going to be n factorial x minus 1 to the n. And if I divide that, then I'm going to get n plus 1, x minus 1. So my row value, here incidentally I simplified rather than, what did I do in C part? In C part I plugged them in and then simplified. I decided to simplify before I put it into my row. Doesn't really make a difference. But what do I get here? Well, so this should be my row, if this limit exists. But, well, x doesn't change as n changes. X is sort of nice and fixed, so we can pull it out. It's just a constant. But now the limit of n plus 1 as n goes to infinity. Well, if n is going to infinity, n plus 1 is just one step ahead. And this does not exist, or some people will say that this is infinity. Okay? It turns out the more exact thing to say would be something to the effect of does not exist if x isn't 1, is 0 if x is 1. Because if it is, well then over here you'd get 1 minus 1, and all the terms would be 0. But the point is, my rho is only less than 1 for x equals 1. So the series only converges for x equals 1. Any other value, your rho doesn't exist, and there's, well, doesn't exist or goes off to infinity. I'll say infinity, actually. Might make it a little clearer. So any other rho value, it's just too big. It's not the less than 1 that we like, that we cherish, that we want to talk about. Okay? Alternatively, I guess you could say something to the effect of, well, n factorial, it just grows way too big. It gets too big. We're okay with things like n factorial in the bottom. You know, that's fine. This will converge. But n factorial on the top almost rarely, well, it never works out unless there's something on the bottom that is somehow even more fiendish or sort of entangles with it or anything like that. So this series actually has a radius of convergence of 0. Only the center makes it converge. So this question here, it's false. We have a radius of convergence. You always have a radius of convergence, but it's not 1 over root 2. I don't even know why they would think people would. Maybe they're just banking on the fact that maybe people are just too lazy to bust out root or ratio test to get a radius of convergence. Such a weird radius of convergence, too. Oh well, so that finishes up our, what was this? Oh gosh, I don't even remember. The 2017 Midterm 2. Hopefully this has been enlightening for you. And yeah, that's all I've got to say other than good luck on your Midterm 2, which will look a little different and is a little more involved, a little longer, I would say. But, as I say, good luck, and if you're in my class, I'll see you in class. Have a good day.